I'm new to optical flat inspection, a rank amateur at best, so bear with me as I walk through some of the things I've done to try to better understand the process. We'll begin with some basics of fringe formation. Then we'll combine some CAD modeling I've found instructive with real-world fringe patterns to develop an understanding of both fringe pattern formation and methods of interpreting them. Inspection with optical flats seems pretty straightforward. Just illuminate an optical flat placed over a part under inspection. Tweak things to get an interference fringe pattern, and read the surface contours by interpreting the fringe shapes. Say a gauge block surface looks like this. If it does, it's very flat. But if another gauge block looks like this, it's, well, not very flat. While it's not difficult to make measurements in the 40 microinch range, about a micron, or even better, with a variety of indicator and instrument setups such as these, measurements in the, say, 4 microinch range, a tenth of a micron, can be difficult without very good setups. But it's fairly easy to make measurements to a few microinches with an optical flat, just a transparent piece of fused quartz with at least one surface lapped to about a microinch. And optical flats are useful for jobs beyond just flatness measurements. They can be used to measure parallelism, dimensions, taper, and even surface finish. Getting really basic, let's talk about the sometimes sensitive subject of length units. Regardless of your preferred flavor, inches or meters, when we get down to really small measurements, some flexibility may be worthwhile. Much of the older literature discussing measuring to millionths is often referring to millionths of an inch or microinches, but getting into subjects such as lapping, fine grit sizes are typically measured in microns, millionths of a meter. Here's a graphical illustration of the two. A meter is 39.37 inches. Keeping it simple, a meter is about 40 inches. Let's call a millionth of an inch a microinch and designate it with the Greek letter mu. And let's call a millionth of a meter a micron. A micron is about 40 times the size of a microinch, so a microinch is about 1/40th of a micron. Here's an example of a magnified surface with a 4 microinch dip, with circles representing 1 microinch and 1 micron diameters at the same scale. When thinking of measurements made with optical flats, we're often interested in surface flatness errors of just a few microinches, but only a fraction of a micron. A 4 microinch flatness error is only a tenth of a micron. For such work, a micron seems pretty large. When considering lapping, it's interesting to compare typical grit sizes with the final flatness goal. A 3 micron grit is generally considered pretty fine, but it's large compared to the 4 microinch flatness error. I'll frequently include both units in this discussion, but if only one is given, just multiply a micron dimension by 40 to get microinches, or divide a microinch dimension by 40, or multiply by 0.025 to get microns. Optical flat fringes are created by the interference of light waves. Think of a light wave as oscillations as shown here. In this case, the wave travels from the light source at the bottom toward the observer at the top. Imagine that the oscillations vary between positive values, shown in red, and negative values, shown in black, with the amplitude defined as the difference between positive and negative peaks. The wave travels toward the viewer at the speed of light, so the oscillations occur very rapidly. The peaks enter our eyes at hundreds of trillions of times per second, so we perceive the wave as continuous light with brightness proportional to the wave amplitude. The light's wavelength is the minimum distance at which the waveform repeats. It can be measured between any two adjacent identical points on the waveform, such as here or here. For visual wavelengths, the wavelength corresponds to the perceived color. If the wave consists of only a single wavelength, it's called monochromatic, one color. The yellow helium light, often used with optical flats, has a wavelength of 23.2 microinches, about 6/10ths of a micron. Here are two light waves, A and B. Think of them as being coincident. They really follow the same path, but let's separate them for clarity, just as we will in the following illustrations. The relative phase of the two waves is their relative vertical positions in this illustration. If identical points on the waves are at the same vertical position, if they fall along a horizontal line, the phase difference is zero. They're said to be in phase, as shown at the left. But these relative vertical positions vary at the right. The phases are different. There's a phase shift between the two. The vertical positions of identical points on the waves don't line up. If the two light waves have the same wavelength and are viewed together, remember that we've separated them for clarity, their amplitudes combine arithmetically as shown by the third wave labeled A plus B. If the waves are of equal amplitude and the phase shift is 0, the combination is twice the amplitude of each single wave. But this is only true if A and B are in phase. Let's look at the combination's behavior as we change B's phase relative to A. We'll measure the phase difference in wavelengths as reported here. The phase difference is now 0 and A and B are in phase as before. The color swatch indicates that the eye perceives a bright result. Now let's shift B's phase by 3/8 wavelength. Now A plus B is 1/2 the earlier value, and the perceived brightness is reduced. Let's do that again and watch A plus B's amplitude in the swatch. As we increase the phase shift, the combined amplitude decreases more and the view becomes darker. Finally, if we increase the phase shift to 1/2 wavelength, A and B cancel. The positive peaks of one align with the negative peaks of the other. One is positive and the other negative, so the sum is 0 if the amplitudes are the same, and the combined wave goes dark. This is the condition that produces the center of a dark fringe with an optical flat. Repeating, the combined wave goes from bright to dark when changing the phase shift from 0 to 1/2 wavelength. Now let's add an optical flat and a part under inspection. The setup looks like this on the bench, with a helium monolight above, shining on an optical flat placed on the inspected part. Let's illustrate this graphically. The light shines down the dashed waveform. A portion of the light passes through the flat, and a portion of the light is internally reflected back up at the bottom of the flat as shown here, again offset horizontally for clarity. The remainder of the transmitted light passes through an air gap, strikes the part, and is reflected back as shown here, again offset for clarity. The two reflected waves combine as we discussed before, forming the sum of the two reflected waves, which we view from above. The combined wave brightness is dependent upon the phase relationship between the two reflected waves. Let's remove all but the bottom surface of the flat and the top surface of the part. The bulk of the flat and the part below the surface don't participate in the explanation. The blue horizontal line represents the bottom of the optical flat. The gray horizontal line represents the top surface of the part under inspection, and there's an air gap between the two. In a moment, we'll vary the air gap, which is reported here. Currently, the gap is 1/4 wavelength. The internal reflection at the bottom of the flat and the external reflection at the top of the part behave differently. The reflection at the bottom of the flat continues upward with the same phase as the incident wave at this point. The incident wave is starting to go positive, and the reflected wave does the same. There's no phase shift. This is a characteristic of an internal reflection. But the external reflection from the part behaves differently. Instead of forming a continuation of the positive part of the incident waveform, there's a half wavelength phase shift, with this reflection flipping to the negative part of the incident waveform. Once the reflection reaches the bottom of the flat, its phase adds the half wavelength flip to an additional phase shift of another half wavelength, which is the total path length for a 1/4 wavelength air gap. So, at the optical flat surface, the part's reflected wave is in phase with the reflection from the bottom of the flat. Since they're in phase, they add, producing the maximum brightness of the combined waveform. Now let's increase the air gap to about 3/8 of a wavelength. The reflection from the part changes phase since the path length through the air gap is increased, and the combined wave decreases in brightness. Continuing to increase the air gap, notice the part surface lowering as we do this, further increases the phase shift until we reach a half wavelength air gap, where the two reflected waves cancel and the result is dark, the center of a dark fringe. We don't need to stop here. If we continue to increase the air gap, the brightness increases, then decreases again, reaching minimum brightness, a dark band, at a 1 wavelength air gap. We can continue this getting a new dark band at each multiple of a half wavelength. In fact, we even get a dark band with zero air gap, as seen here. The phase shift at the part reflection is a half wavelength and immediately interferes with the optical flat reflection. So we can think of the dark bands as occurring at planes parallel to the bottom of the optical flat and spaced at half wavelength intervals below the flat. We'll use this information for CAD models that illustrate the formation of interference fringes on modeled parts. This is the optical flat, and these are planes spaced at 1/2 wavelength intervals below the flat. I'm rounding off the precise half wavelength value for helium light from 11.6 microinches to 12 microinches, both for convenience and to accommodate the view angle, which we'll discuss later. At every location where a half wavelength plane touches the top surface of a part, the light reflected from the bottom of the flat and the light reflected from the part surface will cancel, and a dark fringe forms. This generates 3D contour lines along the part surface, with each contour line falling on a half wavelength plane. If we extract the intersection of these planes and the top surface of a part, the intersections represent the interference fringes. We'll use this technique to visualize fringe formation. The model we just used was of a gauge block with a convex surface that's 40 microinches high, about a micron. Actually, that's roughly the condition of this well-worn block. Obviously, with the real gauge block, the convexity isn't visible in the CAD model at true scale. The height of the convexity is about equal to the size of a small speck of dust. Some sources say dust size varies from about 1 to 100 microns. So let's play a trick. The CAD model includes a parametric scale factor that affects only the vertical dimension of only the block's top surface. The block's width, length, and height below the surface aren't affected. Currently, the scale factor is 1. Increasing the scale factor to 200 doesn't help much, but a scale factor of 2000 starts looking useful, so let's try that. From what we've discussed so far, we might place an optical flat on top of the block with the flat parallel to the nominal part surface, as we just saw. In the side view, the plane spacing is scaled with the same scale factor of 2000, so the planes are still spaced at 1/2 wavelength of the scaled model. Just to check the scaling, the convexity of the block surface is a bit more than 1, 2, 3 half wavelength planes high. At 12 microinches per plane spacing, that's 36 microinches, and adding a bit more gets to the 40 microinch height we modeled. In the top view, we see something approximating the interference fringes we'd see with a real optical flat. It's reminiscent of a topographic map, and fringe generation is sometimes compared with a topo map. In this case, the topo map analogy isn't bad, just turned upside down since the bottom of the flat, which might correspond to sea level, is on top. But be careful. This analogy can be misleading in many cases. Still, we can learn something from this example. For this model, we already know more than we would with real hardware. We've seen magnified views of the block. But let's pretend that we didn't have this information and just assume that the flat touches the part here. We'll often designate this contact point in red like this. Now, each closed fringe line represents a line on the surface that's below the optical flat at multiples of a half wavelength. But, and this is a big but, in this case, the optical flat is perfectly parallel to the nominal block surface. Look at what happens to the pattern if we tilt the optical flat just 10 arc seconds. Now, how much convexity does the fringe pattern suggest? We might assume that the high spot is toward the left and the surface falls off about 6 fringes, or 72 microinches toward the right. A big mistake. That's about twice the actual height of the convexity. Let's look at the side view of this model. The flat tilt angle probably seems ridiculous for 10 arc seconds, but think about the vertical scaling. The vertical dimensions are scaled by a factor of 2000, while the horizontal scale is 1. This means that the flat angle run is at true scale, but the rise is multiplied by 2000, so the tangent of the tilt angle scales by 2000. A 10 arcsecond angle becomes about 5.5 degrees with this scaling. This view gives us a better idea of what's happening. At the right, the plane intersections now combine the vertical height of the surface plus the rise of the optical flat due to the tilt. The fringe lines reflect the distance from the flat to the surface, not the height of the surface alone. Forgive the repetition, but this is very important. Fringe lines don't normally represent lines of constant surface height. They are lines of constant spacing between the optical flat and the surface, and for any case where the flat tilts, the flat-to-surface spacing is not the same as the surface contour height alone. It's related, but not the same. The bad news is that it's usually difficult to position an optical flat accurately parallel to a part's surface. The good news is that we typically don't want the flat parallel, and the tilt provides very useful information, but that's getting just a bit ahead of our story. Just for a reality check, here's a real fringe pattern of a gauge block that's roughly 40 microinches convex, not a smooth contour like the model, but in the ballpark. I'm just tweaking the flat angle to see the difference in fringe patterns. Here the flat is fairly parallel to the surface. It's very touchy, and as I tilt in various directions, the pattern changes. It does appear that the surface is high in the central region. There seems to be a fairly large region of near contact. Something's going on beyond just a smooth high spot. But I can tilt the flat to get a contact nearer the edge and get a pattern similar to the CAD model with the 10 arcsecond tilt. If we look at the fringes with the flat close to parallel, we might estimate a 3 to 4 fringe fall-off, so it is possible to get a rough idea of the surface contour, and that might be good enough to identify this as a pretty terrible gauge block. But we can do better than this rough estimate, as we'll see later. Just to drive this point home, recall the fringe pattern of a near-perfect gauge block, a very flat surface. As I tilt the optical flat, varying numbers of fringes form. The surface height doesn't change with each fringe. The multiple fringes are a measure of the tilt of the flat, not the condition of the surface. Here the flat is tilted mostly along the long edge of the block. But if we make the flat as parallel as possible to the surface, all the fringes disappear if there's a very small air gap, say about a quarter wavelength, or the entire surface turns dark if we essentially eliminate the air gap, giving a single dark fringe. That's what we'd expect. The surface turns dark if the air gap over the entire surface goes to 0, as we discussed earlier. In the next video, we'll begin developing rules that are helpful in interpreting fringe patterns obtained with a tilted optical flat. In some cases, we'll find that tilting the optical flat is mandatory, particularly when we're interested in flatness errors less than a half wavelength.